Alright, this is F55, exponential functions with function bases. So in the last section we talked about numbers with exponents that have functions, okay, that are like two variable functions. In this case we're going to have a function in the base and a function in our exponent. And in order to do this effectively, what we want to do is we want to use the natural log to differentiate. And we did a little bit of this before when we had some crazy functions. In this case it's going to make hopefully more sense because it just simplifies our lives. Okay. Alright, so let's do the first one there. Find the derivative of y equals x to the x. Okay, so this is kind of crazy, but we have a base and we have an exponent, and they're both functions. Okay, so one is a function, the base is a function, the exponent is like a function power. Alright, so I want to use the ln. So in order to use ln, I'm going to take the ln of both sides. Okay, so this is the ln of x to the x, which, if we remember ln properties, this is really x times the ln of x, right? So this exponent can come in front because that's one of our rules. So now I take the derivative. So the derivative of this is 1 over y times y prime, because I'm taking the derivative with respect to x, right? And so in this case, this is a product rule. So product rule is just 1 times this plus the derivative of this times that. So x times 1 over x. Okay, so that's just equal to ln of x plus 1 is equal to y prime times 1 over y. In order to get rid of the 1 over y, I got to multiply this side by it. So I get y prime equals the ln of x plus 1 times y. Well, we know y is x to the x, right? So that's x to the x. So that is my answer right there. Ln of x plus 1 times x to the x. Okay, let's work on the last one. Alright, in the second one here, we want to find the equation of the line tangent. So there's a lot of stuff we got to do here in order to find this effectively, and then plug in pi over 2. So I'm going to plug in pi over 2 now to find the y value. If I plug in pi over 2, so this is sine of pi over 2, so that's 1. Cosine of pi over 2 is 0, so 1 to the 0 power is just 1, so y is equal to 1. So that's pretty easy right there. Let's see. Then what do I want to do? Now I want to differentiate it. So let's use logarithmic differentiation. So I take the ln of the left side. That's equal to the ln of the right side to the cosine of x. Now use log rules. So ln of y is equal to the cosine of x times the natural log of sine of x. Differentiate it now. So it's 1 over y times y prime equals, this is product rule again. Okay, so derivative of the first one, so negative sine of x times the ln of sine x plus cosine x times the derivative of this, which is 1 over the expression times the derivative of that expression, which is cosine of x. So this is equal, let's see if I can clean this up a little bit, negative sine x times the ln of sine x plus, looks to be cosine squared x over sine x, and that's equal to 1 over y times y prime. Okay. Then, this is going to be fun. I'm going to solve now, multiply both sides by y, so I get y prime equals negative sine x times the ln of sine x plus cosine squared of x over sine x, and all of this is being multiplied by the y function, which is sine x to the cosine x. And I want to find that value at pi over 2. Okay, pi over 2. So let's see what we get. Sine of pi over 2 is 1, negative 1. Okay. Sine of pi over 2 is 1. The ln of 1 is 0. So that's nice. Cosine squared, that's at pi over 2, that's 0. So it's 0 over 1 is 0. Times, and then this is 1 because we got that from up there, right? So that's 1. So it looks to be just negative 1. So my slope is negative 1, I think. Oh, it's not. Dummy. It's 0. I don't know why. I'll tell you why. Because, okay, this is 0 plus 0. So this whole thing is 0. 0 times 1 is 0. I forgot about multiplying by 0 there. So our slope is 0. So that means that our equation for the tangent line could be y minus 1 equals 0 times x minus pi over 2, which actually comes to be just y equals 1, right? That's a better way to write it, because slope of 0 doesn't really matter, so y equals 1 is probably better. Now the next page, this right here, I'm not going to prove it, but I'm going to talk about what it is. So if I take a limit, okay, and I say the limit as x approaches infinity of 1 plus 1 over x to the x power, and I can rewrite it as a common denominator here. If I actually evaluate this limit at infinity, or as close to infinity as possible, I'm actually going to get a value that's about e, and that's what e is, about 2.71, like 828, something like that. And so the closer and closer and closer and closer you get to infinity, the bigger the number is, the more accurate this is going to be. I'm not going to prove it for you. You can look at your notes. It's about a page-long proof, and I don't want to waste the time. So you can look at it for later if you want, but I'm not worried about it. I'm just telling you this is one way to represent E. It is using limits. But for this video, it's over. Deuces.